Unit 2, Solution of Algebraic and Transcendental Equation. Structure, Introduction, Objectives, Initial Approximation to a Root, Bisection Method, Error Analysis, Regular Falsy Method, Newton's Method, Error Analysis, Secant Method, Method of Successive Iteration, Summary, Exercises, Solution to Exercises. Introduction. We often come across equations of the form x to the power 4 minus 3x cubed plus x squared plus 6x minus 5 equal to 0, or e to the power x plus x minus 2 equal to 0, etc. Finding one or more values of x which satisfy these equations is one of the important problems in mathematics. An equation of the type fx equal to 0 is algebraic if it contains power of x, that is fx is a polynomial. The equation is called transcendental if it contains powers of x, exponential functions, logarithm functions, etc. Example of algebraic equation: 2x equal to 5, x squared plus x equal to 1, x to the power 7 equal to x of 1 plus 2x. Example of transcendental equations: x plus sin x equal to 0, e to the power root over x equal to x, tan x equal to x. As we know, direct methods can be used to solve the polynomial equations of fourth or lower orders. We do not have any direct methods for finding the solution of higher order polynomial equations or transcendental equations. In these cases, we use numerical methods to solve them. In this unit, we shall discuss some numerical methods which give approximate solution of an equation fx equal to 0. These methods are iterative in nature, and iterative methods gives an approximate solution by repeated applications of a numerical process. In an iterative method, we start with an initial solution and the method improves this solution until it is improved to acceptable accuracy. Properties of polynomial equations. 1. The total number of roots of an algebraic equation is the same as its degree. 2. An algebraic equation can have at most as many positive roots as the number of changes of sign in the coefficients of fx. 3. An algebraic equation can have at most as many negative roots as the number of changes of sign in the coefficient of f minus x. 4. If fx equal to a0 x to the power n plus a1 x to the power n minus 1 plus a2 x to the power n minus 2 plus dot dot plus an minus 1 x plus an have roots alpha 1 alpha 2 dot dot alpha n, then the following hold good. Summation I alpha I equal to minus a1 by a0, summation I less than j alpha j equal to a2 by a0 for all I alpha I equal to minus 1 to the power n by a0. Objectives: after studying this unit, you should be able to find an initial guess of a root, use bisection method, use regular falsy method, use Newton's method, use secant method, and use successive iterative method. Initial approximation to a root. All the numerical methods have in common the requirement that we need to make an initial guess for the root. Graphically, we can plot the equation and make a rough estimate of the solution. However, graphic method is not possible to use in most cases. We with to determine analytically an approximation to the root. Intermediate value theorem. This theorem states that if f is a continuous function on AB and the sign of fa is different from the sign of fb, that is fa less than 0, then there exists a point c in the interval ab such that f is equal to 0. Hence, any value c EAB can be taken as an initial approximation to the root. Example 1. Find an initial guess to find a root of the equation 2x minus log 10x equal to 7. Solution. Let fx equal to 2x minus log 10x minus 7. The values of function f are as given in table 1. Table 1, x fx 1 minus 5, 2 minus 3.301, 3 minus 1.477, 4, 0.397. We find f3, f4 less than 0. Hence, any values in 3, 4 can be taken as an initial guess. Example 2. Estimate an initial guess to find a root of the equation 2x minus 3 sin x minus 5 equal to 0. Solution. Let fx equal to 2x minus 3 sin x minus 5. Note that f minus x equal to minus 2x plus 3 sin x minus 5, which is always negative. Therefore, the function fx has no negative real roots. We tabulate the values of the function for positive x in table 2. Table 2, x fx 0 minus 5 1 minus 5.5224 2 minus 3.72783 0.5766. Since f2 and f3 are of opposite sign, a root lies between 2 and 3. The initial guess can be taken as any value in 2, 3. Bisection method. This is one of the simplest method and is based on the repeated application of the intermediate value theorem. The bisection method is defined as follows. One, find an interval AB in which in root lies using intermediate value theorem. To direction the interval AB, let C equal to A plus B by 2. If FC equal to 0, then X equal to C is the root and the root is determined. Otherwise, use the intermediate value theorem to decide whether the root lies in FC or CB. 3. Repeat step using the interval AC. 4. The procedure is repeated while and length the last interval is less than the desired accuracy. The midpoint of this last interval is taken as the root. Example 3. Use bisection method to find a positive root of the equation fx equal to 0.5 e to the power x minus 5x plus 2. Solution. We find that f0 equal to 2.5 and f1 equal to minus 1.6408. Therefore, there is a root between 0 and 1. We apply the bisection method with a equal to 0 and b equal to 1. The midpoint is c equal to 0.5 and f equal to 0.5 equal to 0.32436. The root now lies in 0.5, 1.0. The tabulated values are shown in table 3. The table 3, AB, midpoint C, FA, FB, FC. After 24 iterations, we see that the smaller root can be found in the interval 0.578300476, 0.578300595. Therefore, we can estimate one root to be 0.5783005. Of the first thing to be noticed about this method is that it takes a lot of iteration to get a high degree of precision. In the following error analysis, we shall see method as to why the method is taking so many directions. Error analysis. The maximum error after the ith iteration using this process is given by e1 equal to b minus a mod by 2y. Taking logarithms on both sides and simplifying, we get I greater than equal to log b minus a minus log ei by log 2. As the interval at each iteration is halved, we have ei plus 1 by ei equal to 1 by 2. Thus, this method converges linearly. Example 4. Obtain the smallest positive root of x cubed by x cube minus 2x minus 5 equal to 0. Correct up to 2 decimal places. Solution. We have fx equal to x cube minus 2x minus 5, f2 equal to minus 1 and f3 equal to 16. The smallest positive root lies in 2, 3. Therefore, a equal to 2, b equal to 3, b minus a equal to 1. We need solution correct to 2 decimal places, that is e less than equal to 0.5, 10 to the power minus 2. From 1 we get I greater than equal to log 1 minus log 0.5 10 to the power minus 2 by log 2 equal to minus log 0.005 by log 2, approximate 8. This shows that 8 iterations are required to obtain the required accuracy. Bisection method gives the iterative values as x1 equal to 2.5, x2 equal to 2.25, x8 equal to 2.09, then x approximately 2.09. This is approximate root. Regular Palsy method. Let the root lie in the interval AB, then PA, FA, QB, FB are points as the curve. Join the points P and Q. The point of intersection of these with the x-axis C line is taken as the next approximation to the root. We determined by the intermediate value theorem whether the root now lies in AC or CB. We repeat the procedure if x0, x1, x2 are the sequence of approximation. Then we stop the iteration when xk plus 1 minus xk mod less than given error tolerance. X, Y, 0, A, B, C1, C2, A, C1, C2, C3, X star. Figure regular Palsy method. A, B. The equation of line chord joining A, FA, B, FB is Y minus FA equal to FB minus FA by B minus A of X minus A. Setting Y equal to 0, we set the point of intersection with X axis as given. X equal to C equal to A minus B minus A by FB minus FA, FA equal to A, B minus B, FA. B minus A by FB minus FA, FA equal to AB minus BFA by FB minus FA. If we denote x0 equal to A, x1 equal to B, then the iteration formula can be written as xn plus 1, xn plus 1, f xn minus xn f xn minus 1 by f xn minus f xn minus 1, n equal to 1, 2, dot dot dot. The rate of convergence is still linear but faster than that of bisection method. Both these methods will fail if f has a double root. Example 5. Obtain the positive root of the equation x square minus 1 equal to 0 by regular Palsy method. Solution. Let fx equal to x square minus 1 since f0 equal to minus 1, f2 equal to 3. Let us take that the root lies in 0, 2. We have x0 equal to 0, x1 equal to 2. Then using 2 we get x2 equal to x0, f2 minus x1 f0 by f2 minus f0 equal to 0 minus 2 minus 1 by 3 plus 1 equal to 0.5. f of 0.5 equal to minus 0.75. The root lies in 0.5, 2.0. We get x3 equal to 0.5 f2 minus 2.0 f 0.5 by f2 minus f 0.5. 0.5 3 minus 2.0 of minus 0.75 by 3 plus 0.75 equal to 0.8. f of 0.8 equal to minus 0.36. The root lies in 0.82. The next approximation x4 equal to 0.8 of 3 minus 2.0 of minus 0.36 by 3.0.36 equal to 0.9286. f of 0.9286 equal to minus 0.1377. We obtain the next approximation as x5 equal to 0.9756, x6 equal to 0.9918, x7 equal to 0.9973, x8 equal to 0.9990. Since mod of x8 minus x7 equal to 0.0017 less than 0.005. The approximation x8 equal to 0.9990 is correct to decimal places. Note that in the problem, the lower end of the interval tends to the root and the minimum error tends to 0, but the upper limit and maximum error remain fixed. In other problems, the opposite may happen. This is the property to the regular falsy method. Newton's method. This method is also called Newton-Raphson method. We assume that f is a differentiable function in some interval ab containing the root. We first look at a pictorial view of how Newton's method works. The graph of y equal to fx is plotted in figure. The point of intersection x equal to r is the required root. Figure a plot of y equal to fx, x0, r. Let x0 be an initial approximation of r. Then x0 fx0 is a point as a curve figure. Figure point on the center x0 fx0, x0 r. Draw the tangent line to the curve at the point x0 fx0. This line intersects the x-axis at a new point, say x1 figure. Figure tangent at x0 fx0. x0 x0 fx0 x1 r. Now x1 is a better approximation to r than x0. We now repeat this process yielding new points x2 x3 until we are close enough to r. Figure 3.4 shows one more iteration of this process determining x2. Figure Newton's method x0 x0 fx0 x1 x2r x1 fx1. Now we derive this method algebraically. The equation of the tangent as x0 fx0 is given by y minus fx0 equal to f x0 x minus x0, where fx0 is the slope of the curve at x0 fx0. Setting y equal to 0, we get the point of intersection of the tangent with x-axis as y minus x0 equal to fx0 x minus x0, or x equal to x0 minus fx0 by f dash x0. But this is our next approximation, that is x1 equal to x0 minus fx0 by f dash x0. In iterating this process, we get the Newton-Raphson as xn plus 1 equal to xn minus fxn by f dash xn for n equal to 0, 1, 2 dot dot. Example 6. Find the smallest positive root of x7 plus 9x to the power 5 minus 13x minus 17 equal to 0. Solution. Let fx equal to x to the power 7 plus 9x to the power 5 minus 13x minus 17. We have f0 less than 0, f1 less than 0, and f1, f2 less than 0. Hence, the smallest positive root lies in 1, 2. We can take any value in 1, 2 or one of the endpoint of the initial approximation. Let x0 equal to 1. We have fx equal to 7x to the power 6 plus 45x to the power 4 minus 13. The Newton-Raphson method becomes xn plus 1 equal to xn minus xn to the power 7 plus 9xn to the power 5 minus 13xn minus 17. 7xn to the power 6 plus 45xn to the power 4 minus 13 n equal to 0, 1, 2 dot dot. Starting with x0 equal to 1, we obtain the values given in table. In 0, 1, 2, 3, 4, 5, xn, fxn, f dash xn, xn plus 1. After 6 iteration of Newton methods, we have x6 minus x5 mod equal to 1.2580 92657 minus 1.25 8092767 equal to 0.00000110. Therefore, the root correct to 6 decimal places is r equal to 1.258092657. Possible drawbacks. Newton's method may not work in the following cases. 1. The x values may run away as in figure A. This might occur when the x-axis is an asymptote. 2. We might choose an x values, then when evaluated the derivative gives us 0 as in figure B. The problem here is that we want the tangent line to intersect the x-axis so that we can approximate the root. If x has a horizontal tangent line, then we cannot do this. 3. Might choose an x that is the beginning of a cycle as in figure 2.5. Say again, it is hoped that the picture will clarify this. A runaway, flat spot, say cycle, figure divergence of Newton's method. However, the difficulties posed have one artificial. Normally, you do not encounter such problems in practice. Newton-Raphson methods is one of the powerful methods available for obtaining a simple root of fx equal to 0. Error analysis. Let the error at the nth step be defined as en equal to xn minus x. Then the error at the next step is x plus en plus 1 equal to x plus en minus f of x plus en by f dash x plus en. Explaining in Taylor series, we obtain en plus 1 equal to en minus fx plus en f dash x plus half en square f double dash x plus dot 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 f dash x plus en f double dash x plus dot dot dot. Since x is a root, we have fx equal to 0. Then en plus 1 equal to en f dash x 1 plus half en f double dash x by f dash x plus dot dot f dash x of 1 plus en f double dash x by f dash x plus dot dot equal to en minus en plus en of 1 plus 1 by 2 n f double dash x by f dash x plus dot dot of 1 plus en of f double dash x by f dash x plus dot dot whole to the power minus 1 equal to n minus en of 1 plus 1 by 2 en f double dash x by f dash x plus dot 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 1 of 1 minus en f double dash x by f dash x plus dot 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 equal to en minus en of 1 minus 1 by 2 en of f double dash x by f dash x plus dot dot equal to half en of f double dash x by f dash x of en square plus dot dot. We can neglect the eccentric and higher powers of en as they are much smaller than en square. En is itself a small number. Notice that the error is squared at each step. This means that the number of correct decimal places doubles with each step much faster than linear convergence. We call it quadratic convergence. This sequence will converge if f double dash by f dash x en square of mod less than en mod less than 2 of f double dash x by f dash x whole mod. If f is not 0 at the root, simple root, then there will always be a range around the root where this method converges. If f is a 0 at the root, double root, then the convergence becomes linear. Example 7. Compute the square root of a using Newton's method. How does the error behave? Solution. Let x equal to root a, or x square equal to a, define fx equal to x square minus a. Here we know the root exactly so that we can see how well the method converges. We have the Newton's method for finding a root of fx equal to 0x as xn plus 1 equal to xn equal to f of xn by f dash x equal to xn minus xn square by xn square minus a by 2xn equal to xn square plus a by 2xn equal to half of xn plus a by xn. Starting with any suitable initial approximation to root a, we find x1, x2 dot 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 which converge to the required value. Error at the end step is en equal to xn minus root over a. Substituting, we get en plus 1 equal to en plus root over a whole square by 2 of root over a plus en minus root a. equal to 2a plus 2an plus root over a plus en square by 2 of whole root over a plus en minus root a equal to 2 of root over a plus en of root over a plus en square of 2 root over a plus en minus root over a equal to en square by 2 root over a plus en. If a equal to 0, this simplifies to n by 2 as expected. Here we are finding the root of x square equal to 0, which gives a double root x equal to 90. Since a greater than 0, en plus 1 will be positive provided en is greater than minus root a, that is provided xn is positive, thus starting from any positive number. All the errors except perhaps the first will be positive. The method converges when mod of en plus 1 equal to en square by 2 of root over a plus en of whole mod less than mod of en, or en less than 2 of en plus root over a, which is always true. Thus the method converges to the square root starting from any positive number and does so quadratically. We now discuss another method which does not require the knowledge of the derivative of a function. Second method. Let x0, x1 be two initial approximation to the root. We do not require that the root lie in x0, x1 as in regular policy method. Therefore, the approximation x0, x1 may lie on the same side of the root. Further, we obtain the sequence of approximation as x2, x3. At any stage, we do not require or check that the knot lies in the interval xk minus 1. The derivation of the method is same as in the regular policy method figure. Figure secant method, roots of equation, secant line. The method is given by this equation xn plus 1 equal to xn minus 1 fn minus xn fn minus 1 by fn minus fn minus 1. We compute x2 using x0, x1, x3 using x1, x2 and so on. The rate of convergence of the method is superlinear 1.618, that is, it works better than the regular policy method. Example, with second method to find the roots of the equation fx equal to 0.5 e to the power x minus 5x plus 2. Solution, we have f minus x equal to 0.5 e to the power minus x plus 5x plus 2 greater than 0 for all x, hence there is no negative root. We obtain f0 equal to 2.5, f1 equal to minus 1.6408, f2 equal to minus 4.3055, f3 equal to minus 2.9572, f4 equal to 902990, fx greater than 0 for x greater than 4. Therefore, the given function has two roots, one root in 0, 1 and the second root in 3, 4. For finding the first knot, we take x0 equal to 0, x1 equal to 1 and compute the sequence of approximation x2, x3. For finding the second root, we take x0 equal to 3, x1 equal to 4 and compute the sequence of approximation x2, x3 dot dot. The results are given in table 5. Table 5. xn minus 1, xn, xn minus 1, xn, xn plus 1. The two roots are 0.57830058, 3.4017958, correct to all decimal places given. Method of successive iteration. The first step in this method is to write the equation fx equal to 0 in the form x equal to gx. For example, consider the equation x square minus 4x plus 2 equal to 0. We can write it as x equal to root over 4x minus 2, or as x equal to x square plus 2 by 4, or as x equal to 2 by 4 minus x. Thus, we can choose from in several ways since fx equal to 0 is the same as x equal to gx. Finding a root of fx equal to 0 is the same as finding a root of x equal to gx, that is finding a fixed point alpha of gx such as alpha equal to g alpha. The function gx is called an iteration function for solving fx equal to 0. If an initial approximation x0 to a root alpha is provided, a sequence x1, x2 dot 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 may be defined by the iteration scheme. xn plus 1 equal to z of xn with the hope that the sequence will converge to alpha. The successive iterations for solving x equal to e to the power minus x by 3 by the method xn plus 1 equal to e to the power minus x n by 3 is given in figure. Figure successive iteration method. The method converges for some constant m such as 0 less than m less than 1. The inequality mod of gx minus g alpha less than equal to m mod of x minus a hold true whenever mod of x minus alpha less than equal to mod of x0 minus alpha. For if 16 holds, we find that xn plus 1 mod of minus alpha equal to mod of g xn minus alpha mod equal to mod of g xn minus g alpha less than equal to m mod of xn minus alpha. Using this relation recursively, we get mod of xn plus 1 minus alpha less than equal to m mod of xn minus alpha less than equal to m square mod of xn minus alpha xn minus 1 minus alpha less than equal to m to the power n mod of x 0 minus alpha. Since 0 minus m minus 0 limit m to the power n equal to 0, thus limit xn equal to alpha. Condition 16 is satisfied if the function gx possesses a derivative g dash x such that mod of g dash x less than 1 for mod of x minus alpha less than x 0 minus alpha. If xn is close to alpha, then we have xn plus 1 minus alpha equal to g of xn minus g alpha less than equal to g dash e mod of xn minus alpha for some e between x0 and alpha. Therefore, condition for convergence is g dash e less than 1 or mod of g dash x less than 1. Example, let us consider the equation fx equal to x cube plus x minus 2. It has only one root, real root at x equal to 1. There are several ways in which fx equal to 0 can be written in the desired form x equal to gx. For example, we may write x equal to x plus fx equal to gx and write the method as xn plus 1 equal to xn plus fxn equal to xn cube plus 2xn minus 2. In this case, g dash x equal to 3x square plus 2, and the convergence condition is mod of g dash x equal to 3x square plus 2 less than 1 or 3x square less than minus 1. Since this is never true, this arrangement does not converge to the root, and alternate rearrangement is xn plus 1 equal to 2 minus xn cube. This method converges when g dash x mod equal to mod of minus 3x square less than 1 or x square less than 1/3 or a mod of x equal minus mod of x less than 1 by root 3. Since this range minus 1 by root 3, 1 by root 3 does not include the root x equal to 0, this method will not converge either. And the rearrangement is xn plus 1 equal to 3 root over 2 minus xn. In this case, the convergence condition becomes 1/3 mod of 2 minus xn to the power minus 2/3 less than 1 or 2 minus xn whole to the power minus 2 less than 3 cube or mod of xn minus 2 greater than root over 27. Again, this range does not contain the root. Another rearrangement is xn plus 1 equal to 2 by xn square plus 1. In this case, the convergence condition becomes 4 mod of x 1 plus x square of square less than 1, 4 mod of x less than 1 plus x square whole square. This inequality is satisfied when x greater than 1. Hence, if we start with such an x, the method will converge to the root. Let x0 equal to 1.2, then From 21 we obtain the sequence of approximation as x1 equal to 0.8197, x2 equal to 1.1963, x3 equal to 0.8227, x4 equal to 1.1927, x5 equal to 0.8255, x6 equal to 1.1894 dot dot. The approximation oscillate about x equal to 1 and converge very slowly. Summary. In this unit, we have discussed the actual meaning of root. In general, root determination of an equation is a tedious exercise. So to handle such tasks, we have discussed some basic, simple but still powerful methods of root determination. The methods discussed in this unit are bisection method, regular false method, Newton's methods, scan method, and successive iteration method. Exercises. Do this and comment this solution to exercises.